Hi everyone, in this video we're going to discuss those two points from the last video regarding why can I ignore implicit dependence of u on m, and b, why does all of this give me the right gradient at the end with the adjoint state method. As a quick review, we moved this constrained optimization problem where r of u m equals 0 is our residual. When it's equal to 0, that means U satisfies our forward model, to this unconstrained optimization problem where we dot our residual into a Lagrange multiplier P. We want this to be 0 so that we get equivalence and constrain our optimization problem. We'll call this also Q of U, M, and P. And we optimize with respect to this new functional L. How we do that in an efficient manner is we take partials. So this partial means I'm taking a Frechet derivative, but I'm treating all the other variables as independent of. We take this partial, we get state u out. Then we take the partial with respect to u, knowing that u and m are known. We can infer p from that equation. And then finally, to compute the gradient, we can ignore implicit dependence and just take a partial so that this can be done efficiently. So at this point, u, m, and p are known, and that gives us the gradient. At the end of the day, why this works is essentially p is an algebraic, it just gives the algebra to cancel out the right terms. And that's basically how it works. Similar to how Lagrange multipliers work in finite dimensions. So if we assume, we'll just play a game. Hey, what if I were to constrain these two equations? Partial L partial P equals 0. This is also equal to partial Q partial P, and it's equal to R of UM. Just double check this because Q here is just the dot product of R with P, and this does not depend on P. Phi does not depend on P. That's this one is natural, right? We need that to be satisfied. We construct our Lagrangian to just be that dot product. Well, then a partial with respect to P just gives us that equation. So the less obvious one is, why do I have to solve this so-called adjoint equation to be equal to 0? So this part 2 is really what cancels everything, although 1 helps as well, as we'll see. So this is partial phi, partial u plus partial q, partial u. Just keep in mind that that's 0. So now let's make sure that if we took partial Lagrangian with respect to m, question mark, is this equal to the full derivative of phi with respect to m, where now this delta means, okay, we're now taking implicit dependence into it? The answer is yes, and we'll show it here. So let's compute the implicit dependence. Oh, first of all, 1 is satisfied. So if we assume 1 is satisfied, phi of um is equal to phi of um plus r of um, because this is 0, and this is phi of um plus r of um, dotted into p for any p. And this right here is q of um. So I'm just relabeling that. So this is equal to, when 1 is satisfied, of phi plus q. And so now let's just do our partial derivatives here. This is partial phi, partial u, partial m, plus partial phi, partial m, plus partial q partial u partial m plus partial q partial p partial m plus partial q partial m. Okay, so if we go back up here, partial q partial p is 0. That's our residual. So this term immediately vanishes from 1. Okay, and I'm going to we don't need to recolor actually. So let's just simplify a bit. This is partial q partial phi partial u plus partial q partial u. Those both have this term here, partial u partial m, and that's the problematic term, if you recall from the last video. Then I'm going to resample this, so these two are both partials with respect to m. It's phi plus q. Okay, this right here, so note that L is just phi plus q. So I can rewrite this as partial of the Lagrangian with respect to u times partial u partial m plus partial of the Lagrangian with respect to m. Now, we already said that the partial of the Lagrangian with respect to u is 0 whenever 2 is satisfied. So that is 0. That is by condition 2. So this is equal to the partial of the Lagrangian with respect to m. And this overall was delta phi, delta m. So we do get the correct gradient in this way. So you can think about 2 as just essentially killing the implicit dependence on m. Now what cost does that incur? Well, we have to solve the Lagrange multiplier p such that 2 is satisfied. That's the cost. So this is a PDE solve. But like I mentioned in the previous video, that scales better because independent of the dimension, I have to solve these 2 PDEs. At the cost of 2 PDE solves, I can get the gradient. Whereas if I want to compute the gradient here, this is a much more computationally intensive process that doesn't scale as well. Thank you guys for watching.